Look first at alpha decay, and what happens here is that a nucleus emits a helium nucleus. Nucleus of a large atom emits 2 protons, 2 neutrons. And we write our different radiation things in a way that's similar to how you write a chemical reaction. So this is our standard molecule, and we say that, whatever its atomic number was, or whatever its mass number was, is going to decrease by 4 because we're losing 4 nucleons. Its atomic number will decrease by 2 because we're losing 2 protons, and then we label that with the letter of whatever that new atom is, plus this here helium nucleus. Alright. So, for example, let's say we have uranium-238 emitting an alpha particle. The way we write that, we have uranium-238. Uranium's atomic number is 92. And so our mass number is going to decrease by 4, our atomic number is going to decrease by 2, and we also have a helium nucleus. And it turns out, and so we get a 234 and a 90. Atomic number 90 is thorium, TH, and yeah, so that we're looking at a thorium atom that has 90 protons and 234 minus 90 neutrons, so 144 neutrons, and then a helium nucleus. Alright, so what we're going to be using toward the back of your book, Appendix F has a table of masses of different isotopes of atoms, and we're going to be using that to figure out how much energy is being, or how much mass is being converted to energy in this alpha radiation. Okay, so if we look at that table, we can see that uranium has a mass 238.050786 mass units. Thorium, so this is including the protons, neutrons, and electrons of uranium. Okay, so that's why it's not just 238. And this thorium-234 has a mass of 234.043596, and the helium is 4.002633 atomic mass units. These numbers are a little bit off, one because protons and neutrons aren't quite exactly one mass unit, and because there are electrons, floating around as well. So our change in mass is just the mass of the uranium, 238 point a bunch of stuff. I don't know why I put parentheses around that. Minus the mass of the thorium, 234 point stuff, plus the mass of the helium. Put my decimal in the wrong place. That's 4.4 point whatever. And if we stick that into our calculator, we get that we have lost 0.000168 atomic mass units. So this mass is converted into energy. We know E equals mc squared, and this mass minus 0.000168 times, well, one mass unit was 931.5 mega electron volts per coulomb squared. That's our mass times, or not per coulomb, per c squared, sorry, speed of light squared. And that's times the speed of light squared. So that's, I mentioned that it would be convenient to write our mass in this way, and we can see that our c squareds just cancel out. That's handy. And this comes out to 4.273 mega electron volts. And we were using this as change in mass absolute value, so that becomes positive. And so this is how much energy is converted into mass. Now, just for comparison, this is about 6.83 times 10 to the minus 13th joules, which is really, I mean, that's pretty small, but it mostly goes into kinetic energy. And when you have an amount of kinetic energy, you know, the masses we're dealing with are on the scale of 10 to the minus 27 kilograms, and so when you have, you know, that's a much lower exponent than, or much lower power of 10 to the minus 13. So they can be moving pretty fast after this kind of decay.